Driver state and behavior detection through smart wearables. My name is Arash Tawakkoli. I'm a PhD student at University of Virginia Link Lab, and I present on behalf of my co-authors, Shashwat Kumar, Mehdi Bukeshwal, and my advisor, Arsalan Heydarian. Autonomous technologies are evolving exponentially, changing the interaction between semi-automated vehicles and the human driver. Previously, advanced driving assisting systems were only used to assist the driver, who acted as a supervisor. With the fast-paced improvements in autopilot systems, the line between the supervisor and a sole driver is starting to blur. This approach to autonomy is referred to as shared autonomy, in which the task of driving is achieved through a collaboration between the driver and the vehicle. Despite their successes, these approaches still rely on the driver to take over in critical situations, without the vehicle having any understanding of the current state of the driver, such as being distracted. Safe shared autonomy requires accurate driver state models. In order to address these issues, the shared autonomy approach generally includes a driver sensing module, in which the driver's state and behaviors are monitored in real time. Through the driver sensing module, the vehicle is provided with a contextual awareness with respect to the driver's status in real time. Driver sensing systems often rely on camera streams. Cameras are very powerful in revealing drivers' activities, states, and behaviors. However, camera streams suffer from a few hardware, driving, and privacy-related issues. Changes in illumination, having shadows, angle of the camera, and even type of the camera can significantly influence their accuracy and reliability in detecting drivers' state and behaviors. To cover the entire space, multiple cameras have to be used. Cameras are highly intrusive in nature, which may make people feel uncomfortable when being constantly monitored. And lastly, although we have seen significant improvements in computational techniques, processing video streams is still resource extensive. Although recent improvements such as enhancement in night vision capability of cameras or fusing with radar system have overcome some of the aforementioned problems, the issue with privacy intrusion and high computational requirements still remains as main issues with cameras. The aim of this paper is to use passive sensing techniques through smart wearable devices to detect driver behavior and states. These passive sensing methods can be used to, for one, optimize video recording duration to the least amount possible, such as only collecting videos when passive sensing requires additional information. 2, cover situations that vision system cannot capture, such as low light situations. And 3, use less computational energy as compared to video recording. While passive sensing has been studied in driving research, their applicability in real-world driving scenario remains an open question, partly because these technologies are just starting to become popular and emerge as a long-term deployment solution. Now, the question becomes, are off-the-shelf wearables applicable to real-world driving? Let's look at the previous studies. Recent studies have provided insight into the application of wearable devices and ubiquitous computing in driving studies, which primarily focused on various states of the driver, such as stress, as well as different driving behaviors, such as takeover readiness. Leo et al. Used a combination of phone and wearable device to detect driving maneuvers, such as a steering wheel turning angle, with an accuracy of 98.9%. Saeed et al. Then analyzed drivers' arousal level in a driving simulator using a wearable device worn on the participant's wrists and achieved a F-score of 0.82 for arousal detection through recruiting 11 participants. Choi et al. Used a wrist-worn wearable device for detecting drivers' stress, fatigue, and drowsiness. By using a driving simulator, they were able to achieve an accuracy level of 98.43% for detecting each state. Goel et al. Used a wearable smartwatch to detect instances of driver's distraction in driving simulator. Bai et al. Used a wearable device on a phone for detecting driver's distraction based on driver's hand movement. By using the IMU sensors on the wearable device, Lee et al. Was able to detect different classes of phone, text, drink using a touchscreen and normal driving with an F-score of 0.87. Hong et al. Used a smartwatch and a wearable magnetic ring along with eye tracking glasses to detect driver's distraction and activities in an on-road controlled study. Lastly, Kondinger et al. Used off-the-shelf wearable devices to detect driver's drowsiness in a driving simulator. In their study, authors have used heart rate signals for drowsiness detection and achieved an accuracy of 99.9%. Let's look at the gaps. Most of the past studies were conducted in simulated environment or through controlled experiments. This can become problematic because most of these studies may lack the proper ecological and external validity to allow their findings to generalize in real-life contextual settings where real-world challenges and noise exist. Additionally, most of these studies have only leveraged the IMU sensor on the smart wearable for driver behavior detection, leaving all the other sensors such as heart rate or PPG or even light unexplored. Furthermore, as opposed to most of these studies that used wearable devices that were designed specifically for the study, we are interested in exploring ubiquitous sensors such as off-the-shelf smartwatches for driver state and behavior analysis in the wild. This is due to the fact that these devices are already used by drivers and participants in their daily lives, and they have multiple sensors built into them. Now let's look at our methods. To address these gaps, we took advantage of a study that we already conducted for collecting drivers' physiological data in real-world naturalistic conditions, titled Harmony. Harmony is a framework that is leveraged to collect drivers' behavioral and state measures together with environmental sensing through physical devices such as cameras and wearable devices, as well as virtual sensors such as computer vision algorithms or APIs. Within the current Harmony dataset, 21 participants' vehicles are equipped with a dash camera which records both inside and outside of the vehicle as the car turns on, as well as a smart wearable is given to them which is equipped with an in-house app, namely Swear. Swear facilitates the process of data collection on smartwatches by adding the ability to control each sensor's data collection frequency. Here is a sample vehicle equipped with Harmony. Now let's talk about our framework. We have chosen a random subset of the collected data for the purpose of this study from 15 participants within Harmony. We use the in-cabin and outside-facing videos for manual annotation of drivers' activities, outside events, and environmental attributes. For this purpose, we have divided up drivers' activities into working with mobile phone, checking sites, checking speed stack, checking sensor stack, eating or drinking food, searching for an item on the passenger seat, touching face, and singing and dancing. Outside events consist of passing an intersection, staying behind a traffic light, being stuck in a dense traffic, and changing lanes. The road conditions are divided into city streets, 2-lane highway, 3-lane highway, parking lot, and merging ramps. Additionally, we inspected the aforementioned categories prior to classification for visual observation of differences in sensor readings. This helps investigate how sensing data fluctuates across these settings and lay the ground for the feasibility of classifying them through machine learning algorithms. For instance, driver's heart rate follows different distributions when performing different activities. This can be seen on the differences between the heart rate peak of singing and food-related categories. In order to perform feature extraction, we analyzed the duration of different activities to find the correct sliding window to be 1 second. Additionally, a 50% window overlap is used to avoid correlation between samples. In order to perform feature extraction, we leveraged tsFresh package on Python to retrieve multiple time and frequency domain features. Because the frequency of different activities varies across different driving scenarios, the dataset has an imbalanced nature. To solve this, we have 1. Balance the data classes by weighing each class to be inversely proportional to its frequency in the dataset. And 2. We have used oversampling based on synthetic minority oversampling technique or SMOTH to generate new samples for the minority class. SMOTH generates new data points from convex combination of nearest neighbors. We apply SMOTH only on the training set. This is important for keeping the classifier unbiased towards new samples. Now let's look at our results. 3 different models were built using random forest, decision trees, and extra decision trees classifier. Random forest outperforms the other 2 models through a tenfold cross-validation with an average F1 score of 90.99% on the imbalanced dataset. This model does relatively poorly on the 2 categories of searching for an item and working with a center stack display. The searching for an item category is mostly due to the lower amount of available data. However, the center stack category may be mistaken with the checking size category 20% of the time. We suspect this is mostly due to the fact that the participants' body movements are very similar when working with the center stack and checking different sides. To further confirm this, we performed a smooth oversampling on the training set and trained a classifier on the oversampling data. It is recognizable that the accuracy of detecting the searching for an item category increases significantly, while the center stack detection accuracy does not increase as much. For classifying outside events, the random forest classifier achieves an average F1 score of 97.68. Using Smooth, we can further increase this to 98.26%. Similarly, random forest outperforms other methods in detecting the road type with an average F1 score of 93.62 and 97.68 for the original and oversampled data respectively. Due to the lower amount of available data, the model performs relatively poorly on the driving in a parking lot and driving on ramp categories. Additionally, it is noticeable that each modality of data adds information to the classification task. We emphasize on this attribute of current off-the-shelf smart wearable devices, as previous work were mostly focused on laboratory-built devices lacking multimodal sensor data built into one device. Smartwatch multimodal data has the potential to reveal different aspects of driving behavior and activities, such as movements, underlying state of the driver, such as stress, and environmental attributes. Note that with the current developments in ubiquitous computing devices, multiple other sensors, such as the skin temperature, can also be used, which are already built into the more novel smart wearable devices. While one sensing modality might not be able to provide all the information to detect certain activities, other sensing modalities such as IMU may still provide crucial missing information to aid the classifier. As a result, by having access to different modalities, we can identify different activities and events with higher accuracy. This has also been shown in our previous work, that certain environmental events might leave a driver's visual and behavioral patterns unchanged while affecting his or her underlying state, which can be measured through HR. Our system can be integrated with cameras and other vision systems to provide more accurate detection of drivers' activities and behavior. Previous studies have developed deep learning-based methods for classifying drivers' activities and behaviors, as well as outdoor events using video cameras when the lighting conditions are suitable. The integration of ubiquitous computing in such systems through sensor fusion techniques can help in edge cases of vision system applications, such as low illumination condition, and in cases that video streams are not available. For example, by integrating smartwatches into vehicles, a user can request between two levels of privacy. In a high privacy case, drivers' activities and behaviors are monitored through the smartwatch, whereas in the other one, it can be the combination of cameras and smartwatches. All of these decisions and analysis can also be performed using edge computing devices that are already being used for autonomous vehicles developments. Our work can be improved from multiple aspects. First, by labeling more driving data, we can enhance the accuracy of our method for driver activity classification. By having more labeled data, we can also use other classification methods that require a higher amount of data, such as deep neural networks. Additionally, we will build and implement a system that can perform the modeling scheme provided here, either on the watch or using an embedded system in the vehicle, to optimize our system for real-time applications. This can also help us make our system more human-centered by incorporating users' feedback in real time. Lastly, we will continue to test newer wearable devices to increase our number of sensor modalities, which can further increase the accuracy of our system. Thank you for listening to my presentation, and contact us if you are interested in our research. uvabrainlab.com